Hi, this is Dr. Chin, and I am creating a video tutorial for completing your CFA assignment for PY 557 or psychometrics. So to get started on your CFA assignment, I'm going to show you how to do an example assignment, and I put the resources in your Moodle page. So let me show you where that resource is. So if you go to the class website and go down to R Markdown CFA, click on example, you'll see a bunch of files in here. If you click download folder, it will download those files into your computer, your local hard drive. You probably need to unzip it. In my case, it did it for me automatically, but if it doesn't, you'll need to unzip it and open up the contents of that folder. Now, I've already downloaded the contents of that folder into my hard drive prior to this. So I'm just going to go straight to that folder. There you go. Okay. And so you'll see a couple of things. You'll see, for example, the syntax that I'll be using for this example. If I click on CFA Example Scale, this basically gives you a description of the scale in which you'll be doing the CFA on. Specifically, this is a scale that measures various competencies related to romantic competence. Now, in this particular demonstration, I'm actually going to be using an artificially generated data set, which is different from the original data set that we use to publish this measure that we had initially developed. But we'll do the CFA based on the hypothesized factors over here. Specifically, I believe there are 9 factors that that we believe this measure would tap into in regards to romantic competence. We're looking at the relationship locus of control, perspective taking, romantic agency. Now, the parts that are highlighted in yellow are the parts that are reverse coded. Intimacy avoidance, emotion regulation, temperament, as well as conflict resolution skills. And the item numbers are in parentheses here, RC1 all the way to RC5. And the response format is 1 through 5. Although again, as mentioned in this example, we're working with an artificially generated data set where I was not able to set the mean intercepts. And so the range of the raw scores in this artificial data set may not be 1 through 5, but nonetheless, we can recreate the variance covariance matrix part of the model. So if you click on the CFA example, it is going to show you or give you a description of the scale. If you double click on this syntax right here, it will open basically the syntax that we will be using for this example. If you click on CFA example generated 11/15/2020, you'll see here that this is the data set ranging from RC1 all the way until RC41. Notice that we're skipping a number of items here, such as we're going from RC5 to RC8. And part of the reason is because we did an exploratory factor analysis before and eliminated some items, which you should always do an EFA prior to doing any type of CFA. Let's see here. This is the example knitted document that we will be reproducing at the end of this video demonstration. And this is the measurement diagram. I can get it to open. Let's give it a second, it's thinking. All right. So for your CFA assignment, I'll be asking you to create a model measurement diagram to give people a visual of the latent factors and the indicators and the pattern of indicator factor loadings, as well as the pattern of unique errors and unique error covariances, so that it'll be easier for people to visualize what is the measurement model for your instrument, or at least the final measurement model. That's pretty much it. So what I'll do, or at least what I would recommend, is if you are practicing this for the assignment, that we will just simply work on the grading rubric for the assignment itself. So if you click on assignment, you go to CFA assignment instructions revised, you see the grading rubric over here, and basically walks you through step by step for the most part. So what we'll do is we will, we will take these steps right here, copy it, let's go back to R, start from a clean slate, go to File, New File, and R Markdown, CFA Example Video Tutorial. That'll be the title that I'm putting in, but you can put whatever title you would want. The output is going to be Word because we want to knit it together as a Word document later on. Go ahead and delete most of this stuff right here. All right, so let's paste the steps in the grading rubric right here. Okay, so first of all, we need to set the working directory. Actually, before we do that, we probably want to save it as well. Notice here that it says Untitled. If you want to save this, click Save As. To save this somewhere else. Video tutorial CFA example. Okay, now it's saved. All right, so first of all, you want to set the working directory. Let's insert a chunk. So you go to Insert and click on R. And because R Markdown is able to work with a number of different software, it's not just R, but it will work with R. So to set the working directory, type in set WD, and we'll need to put in the directory. Now, in my case, it is embedded deep within my computer here. So I'm just going to click on any of the files, or to make it simple, let's click on the data set because that's what we're trying to import here. Right click on that and click Get Info if you're using a Mac. If you're using a PC, you want to click on Properties. You'll see the location right here. See how it looks like. So the nice thing about a Mac is that it largely reproduces the syntax for you. If you did this in a PC, you might need to change the backslashes into forward slashes, and make sure you add a forward slash at the end of the path directory as well. Let's go ahead and paste that. We need to add opening and closing quotation marks. See if this works. All right. There you go. If there aren't any issues in the console, that probably means you did it right. Next is to import the file into the global environment. Master. Use the read.csv function and the name of the data set. Oops. Copy and paste. That's the name of the data set. Make sure you end it with a CSV as well. So we've got 450 observations to 29 variables. I would double check this by opening up the Excel document, which is right here. RC1 through RC41. If you count this is 29 variables. Scroll all the way down. We have 450 variables. It says 451. That's because the first row are the variable labels. So that looks about right. Some descriptive statistics. Not just to figure out how much missing data, but just to get a sense of the raw data. Summary. You can call it master now, because we've just imported the file into the global environment. And you see RC1 through RC41. Again, notice that the minimum and maximum is different from the Likert scale of 1 through 5. That's because we're working with an artificially generated data set where I wasn't able to set the mean intercepts. But nonetheless, if we're working with a real data set, you should see the range of, say, if you're using a Likert scale, the range of your response choice is being represented over here. Here's another way to view the data. Use the view function. Make sure you capitalize V if you're using the view function. That's one way for you to scroll through your data. I get the variable names, static names, and these are your variable names. So next step is to identify any multivariate outliers. Let's run, I don't know, it's formula. So I'm inserting a chunk. I'm going to call this object Mahal. Call this whatever, but I just usually call it Mahal. The function is Mahal Novus, followed by the name of the data set. And we are extracting the column means, and we are extracting the covariances of the data set. Just like that. Now that we have an object called Mahal, let's get a summary just to get a sense of what are the values. Basically, what it's doing is that it is creating a Mahal Novus value for every single person based on all 29 variables in your data set. And it does the calculation based on the specific means for each variable, as well as the various covariance matrix of those variables. So now every person, if you can kind of imagine in your head, there's a new variable sort of added into your data set called Mahal, which is basically the Mahal Novus value for each person. This value tells you how strange or how different this person is from the rest of the data set based on their values on all 29 variables. If someone is statistically significantly different from everyone else in terms of p less than 0.001, then the usual convention is to exclude them because we're suspecting that they may not be a part of a population in the very first place. So let's get a summary. I'll know its values. So the values, the Mahal Novus values range from 12.3 to 53.80. Let's calculate the cutoff score. Let's call this object cutoff equals to Q chi-square. That's the function Q chi SQ. We're taking 1 minus 0.001. So basically, we're counting the chi-square value for the probability of 0.999, which is the inverse of 0.001. The degrees of freedom is 29. If you're lazy to count that, just type in the number of columns. Only if your data set only has the variables for your measure. If you did have any additional variables in your data set, such as if you wanted to do an MG-CFA or a mimic analysis where you have other variables such as, I don't know, race or gender or whatever other variables that you might want to regress on your factors, you shouldn't use n columns. You should just type in the number of items that you have in your data set, which is going to be the degrees of freedom for this cutoff score. So cutoff cutoff value is 58.30117. That means that any person that has Mahalanobis values bigger than 58.30117 is considered statistically significantly different from the rest of everyone based on their scores on all of the on all 29 variables. So how many people do we have who exceed a cutoff score? You can kind of conclude from this that really no one. But if you needed to, if you wanted a quick and easy way, in case if you did have a bunch, say a few people above the cutoff score, you could use summary and get a sense of those who have Mahalanobis values bigger than the cutoff score. And it says here that basically everyone meets that criteria, not surprisingly. If you needed to remove multivariate outliers, you could call this new data set no outliers equals to, and we're going to use a subset function. We're basically creating a new subset from the data set master, where we only want people who have Mahalanobis values that are less than the cutoff. Again, I didn't need to do this for this particular demonstration, for this particular data set, but I'm just showing you the syntax of doing it in case you needed to do so. All right. So now that we know that we're good in terms of multivariate outliers, and by the way, one thing which I am not showing in this demonstration is how to deal with missing data. In this particular data set, there were no missing data. That's why I'm not dealing with that right now. In fact, if you did have missing data, it should have shown up when you had requested for the summary of your data set. I'll refer you to the other tutorial video that talks about the data preparation and screening steps if you wanted to learn how to deal with missing data. So now we have figured out that we are good in terms of not having any multivariate outliers. Let's see how we're doing in terms of multivariate normality. The reason why we test this is because there are certain estimators, or commonly used estimators, such as maximum likelihood, that rely on the assumption that your data is distributed normally in a multivariate sense. So if you wanted to use an estimator like maximum likelihood, you want to check to see if your data set does meet that criteria in terms of multivariate normality. So to do that, first we need to load the multivariate, the MV norm test package. If you haven't installed this already, you want to type in install.packages, followed by open parentheses and open quotation marks MV norm tests. I already have this in my data set, so I'm just going to go ahead and load the library. MV norm tests. Now, to work with this particular library, we need to transpose the data to make the rows be variables as opposed to the columns be variables. Right now, the way it's set up in the object of my no-out data set, the columns are variables and the rows are people. To work with the MV norm tests package, we need to basically transpose that. So we're going to call this object, let's just call this M. M equals to transpose, so negative T for my no-out data set. Sorry, not negative T, what am I talking about? M followed by the arrow pointing towards M. So basically, the function is T, and I'm transposing my no-out data set into an object called M. So let's try that again. That looks better. Let's produce the multivariate normal QQ plot, which the function is QQ norm for the data set. Thinking, and basically what we're doing is we are graphing these theoretical quantiles that are coming from a multivariate normal distribution together with the quantiles obtained from our data set. And if our data set does meet the assumption of multivariate normality, it should correspond pretty well with our theoretical quantiles. You'll see a nice clean diagonal here, which is pretty much what we see. If you want to inspect a multivariate normal histogram, you'll need to load the R companion package. You want to use the install.packages function if you haven't installed it yet. Because I have it installed, I'm just going to load the library. Let's produce the multivariate normal histogram. So the function is plot normal. Notice that N is capitalized and H is capitalized. No out data set. This is false because we want the y-axis to be frequencies as opposed to probabilities. So something's going on. Okay, there you go. Zooming in. This is the multivariate normal histogram. And as you can see over here, in terms of multivariate normality, this is about as normal as you can get. Again, the reason why this is so clean is because this is an artificially generated data set. If it is skewed in any way, shape, or form, you probably want to transform it. Or use an estimator that is robust towards violations of multivariate normality. I'll refer you to my other video tutorial on data screening and data preparation if you wanted some help with transforming your data. So for this one, we're just going to focus on the CFA. All right, so provide the interpretation of whether multivariate normality assumption is met and how you might deal with that. So basically, we'll just say that visual inspection of the multivariate histogram and multivariate normal QQ plots. QQ plot suggests that the multivariate normality assumption is met. The CFA will proceed with maximum likelihood as the estimator for model parameters. Since I'm doing this, let me show you the write-up as well, or at least the relevant parts of the write-up here. Let's click on okay, scroll all the way down. So far, we have covered the first paragraph, where we're talking about how many people we have in our data set, and we're describing the measure, and we talk about how there's no missing data. We calculated Mahalanobis values, but no participants were identified as multivariate outliers, and visual inspection of the multivariate, not univariate. QQ plots and histograms suggest that the multivariate normality assumption was met. Because the study had sufficient sample size, we have about a 450, I think, not 405, so that's a typo. Because we had enough people, generally you would want about 10, at least 10 participants for every item that you have. Given that we had 29 items, you probably will want at least 300 people in your data set. We have 450. Given that we got enough of a sample size, our indicators were, they approximated interval level scales because they're Likert response choices. Data was multivariate normal. It's fine to go ahead and use maximum likelihood as the estimator. So that's kind of where we are right now, this whole paragraph. Okay, so let's delve into the CFA. First of all, you need to load a couple of libraries. Again, I'm just going to load them into my system because I have them installed already. To run the CFA, you need to load Laban. And to create some of the measurement diagrams for us to visualize, just to have a rough idea of how the model parameter looks like, how the measurement model looks like, you'll need to load the semplot package in order to create those measurement diagrams. All right. So let's create the factor model. Now, you may recall, as mentioned earlier, that we were supposed to have 9 factors right here. Relationship, locus of control, perspective taking, all the way to conflict resolution skills. So let me pull this to the screen. So we're going to create an object called 7, not 1. Is it 7? Is it 9? 1, 2, 3, 4, 5, 6, 7. I guess it's 7. I don't know why I thought it was 9. 7. We call this the 7th model, and starts out with an equal sign. And it's the you're going to open this up with an apostrophe. It's called the first latent factor locus. That stands for locus of control. Equals and tilde basically means that locus of control is the latent factor for the following items: RC1, RC2, RC3. Let's see if I can. RC4 and RC5. Make this in the next line so it's easier to see. Perspective is going to be latent factor for RC35, RC36, RC37, RC38, RC39, RC40. Romantic agency. And by the way, you can call these latent factors whatever short forms you would want. Romantic agency is RC8, RC11, RC12, RC41. Intimacy avoidance, RC19, RC20, RC27. Emotion regulation, RC21, RC22, RC24, and RC25. By temperament, RC14, RC15, RC16, and RC30. Last but not least is the conflict resolution skills, RC31, RC32, and RC34. See if I got this right. Locus of control, RC1 through 5. Oops. Perspective, 35, 36, 37, 38, 39, 40, RC8, 11, 12, 41, romantic agency, intimacy avoidance, 19, 20, 27, emotion regulation, 21, 22, 24, 25, temperament, 14, 15, 16, 30, C31, 32, and 34. Now, other things that are not explicitly described here in this particular syntax is it is going to assume that your factors are correlated with one another. It is going to assume that your indicators are that the unique errors of your indicators are not correlated with each other as well. If you need to change some of those configurations, I would encourage you to, I'll upload a tutorial for Laban that will basically show you the language for being able to specify those model parameters. But for this particular simple model, all the latent factors are allowed to correlate with one another. The error variances for each indicator is not allowed to correlate with one another. They're assumed to be independent. And as we do this example, you'll see how we'll make some respecifications along the way. Some of it might include changing the pattern of indicator factor loadings, as well as adding correlated errors. So that is the factor model. So let's run that factor model. 7.fit, because that's what we're going to call it. We're going to do a CFA. CFA is the function on 7.model. 7.model is the model that we just created earlier, using the data from the NOAA dataset. Okay. Let's create a measurement model. SAMPAX is the function. P is capitalized on the 7.fit model that we just ran. Now, what labels, I'm going to specify this as standardized or STD, because I basically would prefer the numbers on the measurement model to be fully standardized model parameters. There are different kinds of layouts that you could use for SAMPAX. We're going to use the tree layout because this most closely corresponds to the typical way in which measurement models are described in the SEM literature, with the latent factors at the very top and the observed measures at the bottom. So let's run that and see. Oh boy. Okay, let's see here. So this is how the computer is sort of reading the syntax that you just wrote, or the model that you just created. So again, 1, 2, 3, 4, 5, 6, 7 factors. And you notice here that the numbers are kind of squished together. You might be able to change some of it. Honestly, I'm not too skilled when it comes to manipulating the measurement diagrams in here. I typically use PowerPoint because it's just so much simpler. And plus, with all this interfactor correlations, it's going to be pretty tricky to get all this to pop out the way you want them to. We might be able to make some changes here. Like we could change, for example, the labels, the size of the labels. There you go. It pops up for me. Let's just make this 0.80 and see how that works. If that made it better or if that made it worse. Yeah, that probably made it worse. So let's go back to what it was before. We could try to mess around with the margins as well. So this goes from bottom, left, top, right in terms of the margins. Don't think that made a big of a difference. Actually, I think, oops, try that again. Basically giving it more space, but I don't think that's working out really well. Anyways, it's just to give you a visual. If you are interested in learning more about how to use SAMPAX, I would encourage you to look at the manual that's out there in regards to SAMPAX. But I typically like to use this, so I have an idea or a rough idea on how many factors I'm creating over here, as well as the number of indicators that load on to each factor. All right. So first of all, we need to check for Haywood cases. This is unlikely to pop up given this is an artificially generated data set, but Haywood cases are basically model parameter estimates that are outside the range of what is logically admissible. This happens due to if you're dealing with small sample sizes, if your model is grossly misspecified, if you have any data entry errors. What happens is that as you force your computer to estimate model parameter estimates for, say, a model that is grossly misspecified, it'll force your model to basically create values that are outside the range of what they should be. For example, you see variances that are negative, which that does not make sense. If you look at the formula for calculating variances, it cannot be negative. We'll look for R squares that are more than 1, because by definition, R square has to be between 0 and 1, because it tells you, it gives you a sense of how much variance is explained in variable y by variable x. We can also look at your standardized factor loadings, assuming you have a congeneric indicator. Assuming you have a congeneric model, basically where each item is only allowed to load onto one factor, your standardized factor loading should not be more than 1. It should range from 0 to 1, or from 0 to -1. So we'll check for those types of Haywood cases. So basically, the error variances, the R squares, and the standardized factor loadings, to make sure that everything is at the very least within range before we would go into examining the model fit. Because if you did have Haywood cases, model parameter estimates that are outside the range of what is admissible, you should not interpret that model. Something is wrong, either with your sample size, with the model, or some type of data entry error, or some other types of issues that might be causing those things. There are other reasons as well, such as having say variables that are too multi-collinear with each other. That happens a lot of times if you have, say, a variable that is basically, say, the total score of the other subscale scores in there, where it's just a complete linear transformation. I would encourage you to refer to the Brown textbook that we use for this class to refresh your memory on those things. So how do you check for Haywood case as well? Basically, you will need to pull up the parameter estimates. So let's use a summary function. Sum.fit is the model that we just created. Standardize equals true, because we want the standardized values. If not, it may not give you. And we want R squared equals true, because we want the R squares as well. So R squared. You can see that the R squares are not more than 1, so that's a good thing. This gives you a sense of how much variability in your indicator, like RC1, is explained by the latent factor. So again, should not be more than 1. If you look under variances, these represent error variances, and these error variances should not be negative by definition. I think we're good in regards to that. In terms of, and covariances represent the covariances of the factors on each other. And the part here under latent variables, these represent the factor loadings. The estimate represents the unstandardized factor loadings, given that R uses the method indicator to set the scale of the latent factor. The unstandardized factor loading for each first indicator on each item is set to 1. We're looking at the standardized, fully standardized factor loading. So that's under std.all. And the values under std.all should not be more than 1, given that we have congeneric indicators, given that we have the congeneric model. So we're good in terms of model data set. Sorry, in terms of Haywood cases. So this gives us permission to look at the global fit indices. Let's see, overall, how are we doing in terms of recreating the sample variance covariance matrix? So the function here is fit measures with M capitalized. And it gives you a bunch of fit indices. We're just going to look at a couple. We will look at CFI. It is 0.929. As long as it is 0.90 and above, it is adequate. 0.95 and above is good or excellent. TLI stands for the Tucker-Lewis index. It is basically a type of comparative fit index as well, except it adds a penalty for having a model that's too complicated. and it is 0.919. As long as your TLI is more than 0.90, it is adequate. If it's 0.95 and above, then they'll be excellent. Let's look at your RMC, your root mean square error of approximation. This should be below 0.08 for excellent, and less than 0.104. That's kind of okay, but 0.08 is what we should be shooting for. So it is 0.042 with the 90% confidence interval that is also below 0.08. So that's a good thing. SRMR, which is somewhere here, to standardized root mean square residual. This should be below 0.08, and it is below 0.08. So in terms of model fit indices, we're doing okay. We've got CFR and TLI that are adequate, and we've got RMC and SRMR that are in the excellent ranges. Nonetheless, we shouldn't just rely on global fit indices as discussed in class, but sometimes that could mask localized errors restraint. So let's take a look at your modification indices to see if a computer would have any suggestions on how we could improve model fit. Now, be very careful with using modification indices. Don't just change your parameter estimates, or don't just respecify your model based solely on your modification indices values. You want to look at your modification indices values, your standardized estimated parameter change, as well as making sure that you have a good theoretical reason or conceptual reason for making those changes. Now, sort dot equals true because we want to sort it according to the highest the parameter change with the highest MI value to be at the very top, so it'll be easier for us to visually inspect the values there. We'll set the minimum value of your modification indices to 3.84. This is associated with a chi-square value of 3.84 with 1 degree of freedom that is statistically significant. So basically, any suggested change in any suggested model respecification that has a modification index value of less than 3.84 is just not going to show up in our output. We only want to look at those that are statistically significant. Okay, so let's scroll up right here. So it shows you a bunch. And you can see here that adding a factor loading of RC8 on locus of control is estimated to reduce your chi-square value by 182.997. That's huge. Again, 3.84 is the cutoff score. This is 182.997. You also want to look at not just at the modification index, but you also want to look at the standardized estimated parameter change, which is SEPC dot ALL. This represents the estimated value of your parameter estimate. If we were to basically have RC8 be regressed on locus uncontrolled, then the estimated factor loading or the estimated standardized factor loading is 0.691. Typically 0.30 and above is considered a salient factor loading or salient standardized factor loading. And yeah, so the standardized EPC values and the MI value is suggesting that we regress RC8 on locus of control. Now, you want to also make sure that this makes sense conceptually, because you don't want to just add in model respecifications just for the sake of improving the numbers. If you're to do that based solely on the numbers and not take into consideration theory, you are very likely to overfit your model, such that you may do a very good job of reproducing a variance covariance matrix for a sample, but it may not generalize to your population of interest. So what is RC8? Let's take a closer look at your inventory here. RC8 was originally hypothesized to load onto romantic agency, which covers I'm confident that I will have a long-term happy committed relationship. I worry at times that I'll end up alone. I'm lonely. I struggle to find someone else today. What I was saying is that RC8 may be cross-loading on locus of control. So looking at the verbiage right here, I'm confident that I'll have a long-term happy committed relationship. And comparing that with the other items over here under locus of control, you can kind of see how RC8 could be loading onto locus of control. So I think there is some conceptual reason to think that RC8 may be better served as loading onto locus of control as opposed to romantic agency. Now, as much as possible, we don't want to add cross loadings. And so my suspicion is that if we were to let RC8 load onto locus of control as opposed to romantic agency, you might be able to get that significant change in model fit. Now, one way to see if this is true is to look at the residual correlations. And the residual correlations basically represent the differences in the estimated variances and covariances between your sample variance covariance matrix and your population variance covariance matrix. Again, all this was discussed in class before. Specifically, we will look at the standardized residual correlations, because the standardized residual correlations are standardized on a scale, specifically their z-scores. And so it's easier for us to eyeball the numbers to see how discrepant are we when it comes to specific elements in our residual variance covariance matrix. So to do that, we're going to call this object z correl, and residuals is the function. We want the residuals for the 7.fit model, type equals to standardize. We want to standardize residuals. Now let me show you a neat trick that we can use with the view function. With the view function, you could, so I'm pulling up, I want to view the z corel object that I just created earlier in line 143. So specifically, let's pull the covariances. So this shows you the variance covariance matrix for RC1 all the way to RC34. And our modification index is saying RC8 should be regressed on locus of control. Now, if this is true, that means that we are probably underestimating the relationship between RC8 and RC1 through 5, because RC8 currently does not have a factor loading on relationship locus of control. So if we were to look at the reproduced relationships between RC8 and RC1 through 5, we should see a large positive standardized residual z-score that is more than 1.96. So if you go to RC8 under the view function, where is RC8? I missed it. Okay, there you go. If you go to RC8, you can sort it if you click on the labels right here. What I do like about the view function is that you can filter it. And if you click on this box that says all, it gives you a distribution of the values. So the range here of your standardized residuals ranges from -4 to 10. And so if you click on the upper end of the distribution, the positive values, it'll pull what those values are. These are the standardized residuals of RC8 on these indicators right here, which is RC1, 2, 3, 4, and 5. RC8. So as mentioned before, because currently RC8 does not have a factor loading on locus of control, we are severely underestimating the relationships between RC8 and RC1 through 5. Now, this probably also means that we are overestimating the relationship between RC8 and some of these indicators here in romantic agency, because we're adding an unnecessary factor loading between RC8 and romantic agency. So if you click on RC8 again and click on the lower end of the distribution, this shows you the value here between -4 and -2. It looks like we are overestimating the relationship between RC8 and RC12, which RC12 is one of the items under romantic agency. So generally, the standardized residuals appear to support the suggestion by a modification index as well. I mean, notice how this is negative 3.05, which is more than the absolute value of 1.96. And notice how this is so different from the rest of the other standardized residuals. The rest of the other standardized residuals are literally less than the absolute value of 1.96. If you see here E times, say, negative 10 to the power of 6, basically, so that's how you would interpret this. You're taking this decimal points and shifting this 6 times, going towards the left. So this is a very, very, very small number right here. If you want to go back and look at the entire variance covariance matrix, you should be able to see that over here too. Anytime you see a +0, that means we're not changing the decimal points. If it's negative and followed by some number, we're moving the decimal points to the left. If you see plus, I'm trying to look for a plus. I guess there aren't any plus. If you see, if at any point you see a plus, say +0.3 or +0.5, then you move the decimal points to the right. All right, so the results of the residual correlations appear to be consistent with the modification index. So for the sake of time, I've already written out the explanation here, so I'm just going to copy and paste. Inspection of these standardized residuals suggested a few localized errors for strain. The largest modification index associated with this MI value and this completely standardized EPC value is suggesting that item 8 should be regressed on the locus of control factor. This suggestion also appears reasonable because one's confidence in having a happy long-term relationship could be influenced by their perception of their locus of control. So a revised factor model with item 8 regress on the locus of control, as opposed to the romantic agency, is going to be examined in the next step. Let's create this new factor model. To do that, I'll just copy this right here. And instead of having RC8 be regressed on romantic agency, have RC8 be regressed on locus of control. That's all we're doing. And let's call this the revised 7 model. Let's run the factor model. Revised.7.fit equals to Cfa is the function. Revised.7.model data equals to no out. Let's create a path diagram. Impact is the function. Revised.7.fit. What labels we want them to be standardized. Layout to be layout. If you get the chance, you should mess around with the different layouts. It's kind of funny to see the different other types of layouts that are offered in SEMPACs. Oops, I think I had a typo here. This is the new model. Oh boy, that looks more right. Let's see if we could. Okay, so I'm going to reset whatever prior configurations were on the measurement model right here. This is dev.off. So it should give us the default settings. There you go. That looks much better. So you can see that now RC8 is now regressed on locus of control as opposed to what it was before. All right, let's check for Hayward cases. Summary function, revise.7.fit. We want standardized values as well in the output, and we want R square. Right. There you go. All right. R square values, none of them are above 1.0, so that's good. Error variances are not negative. And in terms of the factor loadings, which is this column right here, the last column, you don't see anything that's above 1.0. So no Hayward cases, we're good. So let's look at the global fit indices. So CFI is, let's see here, how are we doing in terms of CFI? 0.987, and TLI is 0.985. So this is actually now in the excellent range as opposed to the adequate range. REMC is still in the excellent range, although even it is significantly lower. It is 0.018. SRMR is also still in the excellent range, 0.035. So global fit indices look good. By the way, in terms of the write-up, let me show you where we are right now in terms of the write-up. I can find it. And put the write-up right here. Okay. So previously, with the original model, we inspected for model parameter estimates. Here is explaining the rules that we're following in terms of interpreting the global fit indices. In the original model, the CFI and TLI was a range from acceptable to good. It's a typo here. As mentioned previously before, modification indices and the EPC values were examined. These were the criteria. You need MI more than 3.84, EPC values that are in a large effect size, for example, having a factor correlation that's more than 0.50, or maybe a standardized factor loading that is more than 0.30, depending on what that parameter estimate is. The largest modification index was for item 8 being regressed on locus of control. And this appeared reasonable, so we are revising the factor model. So that brings us to this right now. Now, all of our global fit indices are in the excellent range. Let's look at the modification index. Look at localized errors of strings. Mod indices, revise.7.fit, sort. True, because we want to sort it from small to big values. And we want the minimum value to be 3.84, because that's associated with p less than 0.05. Any suggested parameter change that doesn't have an MI value that is 3.84 and above is not going to be shown in this output. So at the very top, let's see here. RC 24 and 25. Notice here that our estimated MI change is considerably lower compared to what it was before. I think it was 100 and something for regressing item 8 on locus of control. So I'm glad that we did that. But nonetheless, this is still more than 3.84. It is estimated that if we were to allow a correlation of the unique variances between RC 24 and 25, that's going to reduce our overall model. That's going to reduce our chi-square model fit to 13.159 chi-square values. That is more than 3.84. So that is estimated to be statistically significant with 1 degree of freedom, given that we're only changing one parameter estimate. If you look at the estimated size of the parameter, it is estimated that correlation, it is correlation because it is standardized. The correlation between the unique variances of RC24 and RC25 is estimated to be 0.52. Now, typically for correlations, if it is above 0.5, that's a large effect size. So far the MI values and the effect size is suggesting that are adding a correlation between the unique variances of RC24 and 25 might be a good idea. Let's take a look at the residual correlations, because if this is true, this means that we are currently underestimating the correlation between RC24 and 25 in the variance covariance matrix. This is because we are currently lacking a correlated error between RC24 and 25. That means that if you look at the standardized residual correlations, we should see a large positive standardized residual correlation between RC24 and 25. So let's see if that is correct. So zcorrel, the name of the object, and the name of the function is residuals. We want this for revise.7.fit. And we want standardized. That's right. Zcorrel equals to residuals. Revise.7.fit. Type is standardized because we want standardized residuals. Let's take a look. So the two items of interest are RC24 and 25. Currently, RC24 and 25 are regressed on emotion regulation. So like I said before, if it is true that we are missing a correlated error between RC24 and 25, we should be underestimating the correlation between these two variables in the correlation matrix. Let's do filter. Underestimating, that means we should get a positive value. So let's go all the way to the top. So this is hereby showing that the standardized residuals for RC24 with all of the other items in your measure ranges from -3 to +4. So if you click on the largest one, which is from 3 to 4 in terms of standardized residuals, it is RC24 with RC25, just like what we had anticipated. Okay, well, so far the modification indices, the standardized estimated parameter change, as well as the residual correlations appear to support adding this parameter estimate, but does it actually make conceptual sense? Well, let's take a look at the items to figure that out. This is emotion regulation, so this is referring to a person's ability to deal with negative affect when it comes to interpersonal relationships. So this covers I lose my temper, I get into arguments, I often say things I don't mean when I am mad, and I get mad, I do things that I later regret. So looking at the item verbiage in here, I can kind of see how these two items may have a shared covariance with each other over and above the other items here under emotion regulation, simply because the verbiage here is similar. When I get mad, when I get mad. This is referring to when I say things, this is referring to when I do things. So I think there is enough of a conceptual sense to add a correlated error between these two. Again, if for example, if it's something else, like say, for instance, I lose my temper and I get into arguments, like I don't really see how there could be a method effect over here, but between RC24 and 25, I could see how there could be a method effect over here. All right, so in terms of the conclusion so far, I'm just going to copy and paste what I've written to save time. The visual inspection of the model parameter estimates did not reveal the presence of Haywood cases. Global fit indices were excellent. However, the largest modification index and completely standardized EPC value suggested adding correlated error. A correlated error between items 24 and 25. Visual inspection suggests that these items refer to verbal or physical acts that cause regret. Also, the inspection of the residuals suggested an underestimation of the correlation between items 24 and 25, consistent with the suggested revision by the largest MI value. Given these empirical and theoretical reasons, we are going to rerun the model with item 8 regress and the locus of control as before, and incorporating a correlated error between items 24 and 25 to reflect those wording effects. So now notice here in your grading rubric that I'm asking you to create a measurement model. Now, if you do need to revise it again, don't go to this step just yet. Make sure you come up with a finalized model before you create the measurement model in PowerPoint. So I'm gonna copy and paste more headings here from the grading rubric that is under here. So to delete this. Okay. Let's call this modeling revised model with correlated errors. Let's create the model. I'm going to copy and paste from the previous one and just add the correlated error. The nice thing about the modification index output is that it gives you the language for adding the parameter estimate here. So tilde is basically the correlated error between RC24 and 25. Make sure that the apostrophe ends after everything else, not between this line and this line. So RC24 and 25 is not added as another parameter estimate. And let's call this revise correlated error.7.model. Run the factor model. So revise.cor.error.7.fit function is Cfa, and this is the model that we just created. We're going to run this on the no out data. Let's create a path diagram. Same as before, sem.path and sem paths. So now we're changing. There you go, it's giving me the actual model itself. Equals to E for standardized, layout equals to let's see here. So we should be able to see that's it. I wonder why I'm not able to figure this out. Again, zoom. There you go. Whoops. Okay. So RC24 and 25. Notice here that we now have a intercorrelation between RC24 and 25. I know that doesn't look very great. I'll show you how to create a better looking measurement model in PowerPoint. Check for Haywood cases. To do that, we need to pull the parameter estimates. So summary, revise, and we want standardize equals to true, and we want the R square. So R squares, none of them are more than 1. Error variances, none of them are negative. And in terms of standardized factor loadings, none of them are none of them are more than 1. Notice over here under covariances, we have RC 24 and 25 being regressed on each other in terms of their unique error variances. And the standardized correlation between these two unique variances is 0.315. Let's get the global fit indices. So fit measures, oops, chunk first. Measures, correlated errors for the 7-point model. CFI is really good, 0.99. PLI is 0.98. SRMR is 0.035, which is excellent, and RMC is 0.016, with a 90% confidence interval of less than 0.08 as well. The global fit indices are really good. Let's take a look at the Modification Index then. Sort. Value of 3.84. There's a typo somewhere here. Modification indices. Where's that symbol? Where is that symbol? Mod indices. Sort equals true. Minimum dot value. All right. Let's see. So the next change that it is suggesting is regressing RC24 on intimacy avoidance. This is associated with an improvement of model fit of 12.317 chi-square value with 1 degrees of freedom. And the standardized estimated parameter change of 0.139. Now, so this is estimated to be the standardized, in this case, factor loading for regressing RC24 on intimacy avoidance. You may recall that when it comes to standardized factor loading, it should be more than 0.3 in order for it to be salient. So I don't think we should go with this. Even though the MI value is statistically significant, this is not a salient effect size. Similarly, for a lot of these other ones here, I think RC4 being having a correlated error with RC15, the MI value is big, but the standardized estimated parameter change is small. For standardized correlations, for correlations, it should be 0.5 and above for it to be large, and this is 0.179. And given that all of these remaining ones here are basically either correlated errors or factor loadings, it should be above 0.3 at the very least for this to be meaningful, and none of these are above 0.3. So I think we are good in terms of modification indices. Which is why I think this highlights the importance of not just looking at MI values, but also looking at the meaningfulness of the parameter estimate. And not just that, even if you had a meaningful parameter estimate, we should look at theory as well. If it doesn't make sense conceptually, don't re-specify a model. So in terms of the residual correlations, error. Standardized. Specifically, the variance matrix. So overall, I don't see, if you wanted to, you could eyeball the standardized residuals. I mean, I'm looking at this right now, and they're all really small. There's nothing really that's more than the absolute value of 2.00. And so again, given that the modification indices are not suggesting any change, you're probably okay. Not even looking at the localized errors for strains if you don't want to. I usually look at that in order to supplement my investigation of changes that is suggested with modification indices. So in terms of the recommendation here, I'm just going to copy and paste for the sake of time. We examined this revised model with correlated errors. The visual inspection did not reveal any Haywood cases. The global fit indices were excellent, although there might be some strains in the model implied by the variance covariance matrix. Standardized residual variance covariance matrix. Inspection of the MI values and the completely standardized EPC values do not suggest that we should respecify the model. So in the write-up, it's kind of where we are at right now. Basically, that's the entire write-up for the last model. And it answered, please see figure 1 for the final measurement model. Now for the measurement model, you won't be able to copy and paste this into our markdown per se. You might be able to copy and paste this into the knitted document. But to do that, we will need to knit this first. Okay, so let's go ahead and knit this. And while we're doing that, there's some error here. Line 20, what's going on? Maybe this one. Let's try this again. It's this one. No, it's still saying 920. Not exactly sure why it's not knitting right now, but that's not going to be my focus to try to troubleshoot this at this point. I'm just going to pull up the document that I had knitted before, which is this one. All right, so let's show you the PowerPoint measurement diagram here. Okay. So to do this, if you worked with PowerPoint before, this shouldn't be that much of an issue. Basically, you open up a new presentation. And I do not want that. Insert the slide. That's weird. Let's try it again. New presentation. There you go. Basically, you want to know how to create boxes, and you want to be able to create ovals and those arrows. So if you go to insert, and this may look differently for you if you're using a different version of Microsoft PowerPoint, but it's typically under shapes. So you can create a shape over here, and if it comes default with a color, you could change it. Like I'm changing this to no fill. And if I wanted to add, say, a text box into it, and say something like this. All right, so that'll be the latent variable for locus. And if I wanted to add some factor loadings, go to Insert, go to Shapes again, and click on this. So I can add a unidirectional arrow. Now, typically, these lines here should be black as well. That's how most journals typically like them. So I'm going to change them to black. And I'm going to follow the last, this one basically. And let's pull the parameter estimates. A small screen here, so RC1 through RC8. So locus of control on RC1 through 1, 2, 3, 4, 5, and 8. Okay. I'm just going to show you a couple. I'm not going to go through everything. If not, this video might be a really long video. Going to add the indicators. You could just work with a text box and say this is RC1. Change that. And if you wanted, probably should center that. If you wanted to have the box show up, you'll just need to go to Shape Format and click that. Then that's how you get the box. Oops. C1. Just copy and paste that. Change this to RC2. Say, for example, if there was a correlated error between RC2 and 3, just go to Insert, go to Shapes, and click on a bidirectional arrow, connecting one with, actually not bidirectional, we would need a curved arrow. Let's see what we got here. This should be what you need. Let's try that. There you go. Make this black. Something like that. Going to show independent unique errors. There'll be that arrow right there. So yeah, so that's kind of how you create parts of the measurement model. And this here is basically the caption for the figure. First you'll explain what those acronyms mean, and then explain a little bit about how to interpret this. Boxes represent items, ovals represent latent constructs, straight arrows represent factor loadings, and dotted arrows represent error. So I guess I made them into dotted arrows, which I might be able to do that. There are dotted arrows. I might need to go to this, go to Shape Format, and let's go to Format Shape. Compound type, or maybe dash type. There you go. That'll be how you could make them dotted if you want to. And there you have it. These symbols over here, this is the latent Y notation for error variances. You could use delta as well if you don't want to use epsilon. But that's pretty much it on how you could create your own measurement diagram. It looks a lot cleaner, better compared to what I think I was able to create from the R Markdown. So that's pretty much it. So you take something like this, say I'm done creating the figure. I would select everything, I would copy it, and in the Word document, I could paste this as an image. Let's try this. There you go. And it can all be together into your R Markdown document. Okay. Let's go back to R Studio here. Where are you? And that's pretty much how you would do the CFA assignment. I bet you I'm going to save this right now. I'm going to close out of this. No, don't save. See if you can knit it together again. Sometimes there will be weird errors that come up when I'm running an analysis for too long, and just restarting it may help with the knit function. Once again. One last attempt. I think it's the name. All right, what's the new name here? Again. Phone. I know why. Because even though we had set the working directory, I didn't save this in the same working directory of my data set. Let's try this again. The courses. All right. One more time. Because initially, I think I had, just out of expediency, saved the R Markdown document on the desktop as opposed to the same file that the data set is at. So that's why R Markdown was not happy with it. And there you have it. This is the R Markdown file. And as shown just now, once you write up the results in a Word document or something, or even in your R Markdown file, oops, take copy, please duplicate. Yes. Okay. I think I'm going to save it. That's a different name. Oh my God, it's weird. You can copy and paste your measurement diagram from PowerPoint into your file. Where's the clean? There you go. This. And paste it as a picture. If you don't have that, you can go to paste special and should give you a couple of options on how you want to paste it. All right. So I hope that was helpful. Let me know if you have questions, and I hope you have fun with this assignment too. Take care. Bye-bye.